So 15.1, we introduced the concept of functions of several variables. We're taking points to real numbers. We talked about how the notation works, how the graphs work. And then we spent a couple days looking at the limits of functions of several variables. And when we try to look at the limit coming into a point, we can look at certain paths. And we saw some of the challenges we have trying to get a handle of what's going on. So today we're going to start talking about differentiation. And what we're going to do to start off with is talk about partial derivatives. So you might wonder, where's the word partial coming from? Here's the idea. So back in your Calc 1 or AP Calc, the derivative was formulated as a limit. The limit as h goes to 0 of f of x plus h minus f of x over h. And if we look at what this is, just to kind of remind you what the heck, where this is coming from. If we think graphically, we're at some point x, and then we move to some point x plus h, assuming h is positive here. And we look at the slope of this line, this so-called secant line, a line that cuts through these 2 points. We would look at the change in y over the change in x. But since we're looking at the graph of the function y equals f of x, the change in y is going to be, well, the y value at x is f of x. The y value at x plus h is f of x plus h. So this is the change in y. And then the change in x here would be x plus h minus x, which is h. Let me rewrite that there. I got a little... So geometrically, we can think of this as a slope. More generally, we can think of this as the change in the function over the change in x. And by taking a limit as h goes to 0, we're essentially moving this point over here. And the slope of the secant line then approaches what we define to be the slope of the tangent line. And this average rate of change goes to what we define as the instantaneous rate of change. All right. So we all familiar with that story of what the derivative is and why the definition is what it is. So the question becomes, what can we do if we have a function of 2 variables? So z is a function of x and y, and we can do the same thing. The partial derivative of f with respect to x, denoted by this. So we've got this new symbol. Instead of the straight up and down d, df dx, sometimes this is called an ordinary derivative to distinguish it from this notation, this partial notation. This is called a partial because it's in measuring a partial rate of change of f. In this case, we're looking at the rate of change of f with respect to x. So notice what's happening here. X is changing. We're looking at changing the x by how much? By h. We're looking at the change in the function with respect to x. So this is your delta f over delta x. All right? So this is the change of the function with respect to x. But we also have y now. And so what I can do is I can do the same thing for y. I can change the y and look at the rate of change of delta f with respect to y. And so the reason these are called partial derivatives is because they're looking at the rate of change of the function with respect to one variable at a time, treating the other variable as constant. So, what's the geometry of this? So if we're looking at fx at a point AB, this is a notation for partial derivative. That means we're looking at the rate of change of f with respect to x when at the point AB, holding y as a constant. Right? Y didn't change here. We held y as a constant. So a way to visualize this is if we look at y equals b, that plane, and we slice that plane, or slice the surface with y equals b, we're going to get a curve. And that curve here, at the point, the slope of this tangent line here is going to be your fx. So we can think of fx at AB. This is the zx slope. When x equals a on the slice when y equals b. Does that make sense or not? We fix y. So think of taking the surface and slicing it with the plane y equals b. That traces out a curve. And fx is the zx slope. All right, so we'll do an example in a minute. And then over here, the same thing. Here we would look at x equals a, slice the curve that way, and then the slope of this tangent line would be fy at AB. So fy at AB is the zy slope at y equals b on the slice when x equals a. So when we talk about holding the variable constant, that's what we're talking about. We're taking a function of two variables, holding one constant, brings it back to a function of one variable, and then we're basically doing calculus on it. All right? So this is how we take partial derivatives. We could go through the limit definition, or we could just use what we just mentioned here. Let's see how this works. So fx means we take the derivative with respect to x. So that's the first thing. Now we're taking a partial derivative with respect to x. And once again, going back to the definition, when you take a derivative with respect to x, the x is what's changing. The y stays the same. In other words, we treat the y as a constant. All right? So we're going to treat y as a constant. So we've got the same rules of differentiation we've always had. We've got the sum and difference rule. We have the constant multiple rule. 3 is a constant, so what can I do with it? Bring it out front. We're taking the derivative with respect to x. We're treating y as a constant. So I can treat the y just like the 3 and bring that out front too. Oops. Minus, now I've taken the derivative of the cosine of something. What's the derivative of cosine of something? Chain rule says it's going to be minus sine of that thing times the derivative with respect to x of that thing. Now what's the derivative of x squared? Minus a minus. And what's the derivative of x times y? Well, once again, we treat y as a constant. We can bring that out. The derivative of x is 1. And then simplifying it all together, we get 6xy plus y sine xy. So you take the derivative with respect to x, treating y as a constant. So y gets the same treatment as 3. So take a minute and see if this makes sense. Let's take a look at the next one here. Now we're looking for fy. So fy means we take the derivative with respect to y, treating x as a constant. So once again, we have all the derivative properties you know and love still apply. We got the sum and difference rule. We've got the constant multiple rule. In this case, 3 is a constant, but what else is a constant? Since I'm taking the derivative with respect to y, who else gets treated like a constant in the first term there? The x squared. So the 3x squared comes out front. And now I'm taking the derivative of cosine of something. That's still minus sine of that thing, times the derivative of what's inside with respect to y. So once again, in this scenario, the x is going to get treated like a constant and can come out front. So the derivative of y with respect to y is 1. The derivative of y with respect to y is 1. I'm going to get my 3x squared. Minus a minus is a plus. So I'll put my final answer up here and then we'll compare it with what we get down there. So I get my 3x squared plus, I've got this constant x, I'll put that up front, sine of xy. Any questions on these first two examples? Do you see what's happening and why it's happening that way from the definition? We good? All right. Well, you know that you just can't help yourself. Once you take one derivative, you got to take more of them. So how do we take higher order derivatives? Well, we got fxx denoted this way. That just means you take the derivative with respect to x twice. Similarly, fyy, which is denoted this way, means you take the derivative of f with respect to y twice. Now we have these things. These are often called the mixed partials. Right? fxy, now notice here the order, fxy, so fxy of xy, think of that as fxy. In other words, this is the derivative with respect to y of fx. So when you see fxy, it means you first take the partial with respect to x, and then second, take the partial with respect to y. Now the way we would denote this then, using the other notation, is we start off with f. We first take the partial with respect to x, and then take the partial with respect to y. And so this notation, you see it's kind of reversed. But notice that if you look at the letter that's closest to the function, that's the derivative that happens first. And then you move, and then so on and so forth from that. Okay? So for example, if you wanted to do, well, we'll get to that later on, but that's fxy. That's the derivative with respect to x, then y, and then fyx. Once again, you look at the letter closest to the function, so you're going to take a partial with respect to y first, then with respect to x. partial with respect to y first, then with respect to x. So once again, with this Leibniz notation here, you start with the partial with respect to y, and then the partial with respect to x, and then that's what that notation means. Okay, and so we've got that little helpful hint down there to help you remember it. But at the end of the day, you got 4 partial derivatives. Okay, so let's take a look at these. So let's put our original function up here. Oops. 3x squared y minus cosine xy. And let's write down what we had for fx. So fx was 6xy plus y sine of xy. And let's do the 2 partial second derivatives that can come from this. So I could look at fxx. That means I take the derivative with respect to x again. And it once again, I know it's weird because back in AP Calc or Calc 1, if you're taking the derivative of y with respect to x, you pretend y is a function of x. That's not what we're doing here. We're assuming x and y are independent variables. So when we take these partial derivatives, if I'm taking with a derivative with respect to x, I'm assuming that all the y's are what? Constants. So I go through and take the derivative. So once again, I can use my sum and difference rule. I'm taking the derivative with respect to x, so the 6 and the y get treated as constants. I'm taking the derivative with respect to x, so the y gets treated as a constant. Derivative of x with respect to x is 1. So I got your 6y here, plus y times the derivative of sine of something, which is cosine of that thing, times the derivative of that thing with respect to x. Once again, I treat y as a constant. The derivative of x with respect to x is 1. And so my final answer here for fxx is going to be 6y plus y squared cosine xy. Are there any questions on getting this second derivative here? So now we're going to skip down and do number 3 because number 3 is fxy. So we'll start with fx again. So 6xy plus y sine xy. And now fxy of xy means I'm going to take the derivative with respect to y. And if I'm taking the derivative with respect to y, then that means I'm treating who as a constant? All the x's are constants. Okay? So what's going to be the derivative of 6xy with respect to y? What's that term going to work out to be? 6x. Because derivative of y is 1. This is just considered a constant. What rule am I going to have to use to take the derivative of this term? Yeah, we're going to have a product rule because we now have a product of two functions of y. So product rule says I got to take the derivative of the first factor with respect to y times the second factor plus the first factor times the derivative of the second factor with respect to y. So I got my 6x. What's the derivative of y with respect to y? One. So that's just going to be sine of xy plus y times, what's going to be the derivative of sine of xy with respect to y? The derivative of sine of something is going to be cosine of that thing. Chain rule kicks in. What's the derivative of the inside with respect to y? X, which I'll write out front. Any questions on getting to fxy? Do you see what's happening or not, folks? You take the derivative with respect to one variable, treating the other one as a constant. Okay? I'll leave this one to you. So we've got fy from earlier. Fyy means you want to take the derivative of fy with respect to y. And something interesting happens when you look at fyx. Fyx means you're taking the derivative with respect to x of xy. That's the other mixed partial. And it turns out, to your surprise and delight, fyx turns out to be fxy. And the theorem is if fxy and fyx are continuous, then they will always be equal. This is an instance of what's called Fubini's theorem, which is a theorem about integration that we'll talk about in the next chapter. But we can use the integration version of it to come back and then prove the differential version. Otherwise, you can just, I believe you can get the theorem otherwise using mean value theorems. But this says that if you're dealing with continuous functions, the order of derivative doesn't matter. So for example, if I gave you a function f of xy equal to, like, x cubed inverse tangent of the natural log of, y squared plus 1, to the 50th power. And I ask you to find this. Okay? If we would do this in the order as given, we'd have to take 3 derivatives with respect to y, 2 derivatives with respect to x, 1 derivative with respect to y, 2 more derivatives with respect to x, and 1 derivative with respect to y. And look at this. This is crazy. All right. Now, all these derivatives would be continuous, but they're still a mess. However, what Fubini's theorem says is because everything's continuous, I can move all these x derivatives up front. And I can just do all the derivatives with respect to x first, and there's 4 of those. And then there's 5 derivatives with respect to y. But what's going to happen to this function if you take 4 derivatives with respect to x? All of this is going to be considered a what? This would all be a constant. You follow? And what happens when you take 4 derivatives of x cubed? What do you get? You get 0. So that would be 0. So you can use Fubini's theorem to move around the order of derivatives as long as you know the derivatives will be continuous. Right. Okay. So looking at some applications here, we always like looking at applications because remember derivatives in Calc 1, we just did this in Calc 1 last night. Derivatives represent an instantaneous rate of change. One of the most common applications of functions of several variable is a Cobb-Douglas production function. And so here's an example of one. X represents an amount of money invested in labor, so salaries and benefits and things like that. Y represents the amount of money spent on capital investments, so those are things like buildings, machinery, and things like that. And Q represents the amount of units that are going to be produced. So in this particular case, looking at the units, Q represents the units produced in thousands, and X and Y each represent the amount of money invested in millions. Currently, there's $1 million spent on labor and $8 million spent on capital. So the labor amount, that's what the X is. The capital amount, that's what the Y is. How many items are currently being produced? So once again, you plug in X is 1, Y is 8. You get 150, 1 to the 1/3, 8 to the 2/3. You go through your algebra there, you get 600. But Q is measured in thousands of units, so that means that there's 600,000 units are being produced. Okay. So any question on the setup here, what the X and Y measure and what the Q measures? Sketch the level curve Q of xy equals 600. So Q of xy equals 600. So we're going to graph 150, x to the 1/3, y to the 2/3 equals 600. We could graph this on Desmos, but we can actually solve this for y. It's not so bad. Y to the 2/3 would be 600 over 150, x to the 1/3. And what's 600 over 15 work out to be? That goes in nice. What's 60 over 15? That's 4. So this would be 4 over x to the 1/3. So I could have y to the 2/3 is 4 over x to the 1/3. We could get rid of the 1/3 power by cubing both sides. And then since x and y represent the amount of money being spent on things, we can assume x and y are both positive. So I can take the square roots of this. So y squared equals 64 over x. But if x and y are positive, y would be the square root of 64 over x, 8 over root x, which is going to look roughly something like this. Whoops, could draw it. Okay, and we'll fire up GeoGebra here in a minute and show you that. So what does this mean? This is sometimes called an isoquant. So when you see the word iso, it means same. So this is the curve, and on this curve, any point on this curve, for example, 1, 8 is on this curve. I'll put it up here. 1, 8 is on this curve. This represents all the possible combinations of capital and labor that would result in a production of 600,000 units. So isoquant, these are all the combinations that give you the same quantity produced, in this case 600,000. You might see like isotherms when they look at, once again, temperature maps. An isotherm, they connect up all the dots that have the same temperature, and that's how they measure these fronts as they move through. So this is an isoquant. If we wanted to get a picture of this, Rick was in earlier. We were doing some office hour stuff with GeoGebra. Let's see, it was acting up a little bit. Let's see what we can do. Let's do the 600, x to the 1/3, y to the 2/3. And we're looking at, I'm sorry, it's not, it's 150, isn't it? 600 is the isoquant number. And then we'll look at z equals 600. And we'll look at here, we'll try to get the z-axis going here. So we'll go from 0 to, let's say, 1,000. Let's see if it'll do it. It's being a little tetchy today. Looks like we got ourselves a graph. Once again, we're looking for positive x and y's only, because we're talking about money. Let's adjust the x and y's here. Whoops. Only looking for positive here. You can hear the computer revving up here. Boom, there it is. If I look at the intersection of these two things, so I go to Tools, Surface Intersection, click, click. There it is. If I get it straight down, it should be the intersection. So that represents our isoquant, and if I look straight down the axis there, that's what we're getting. Okay. Find and simplify qx and qy. So once again, qx means we're taking the derivative of q with respect to x, keeping who as a constant? So if I'm taking the derivative with respect to x, what's the constant here? 150 is a constant. And then what else is a constant? Yeah, the y piece is a constant. So that would stay the same. I just take the derivative of the x piece. That's going to give me 50, x to the minus 2/3, y to the 2/3. Qy, take the derivative of y, or with respect to y, keeping x as the constant. So the 150 and the x are constant, so they're going to go along for the ride. You take the derivative of y to the 2/3. And there's your qy. Any questions on getting the qx or the qy here? Find and simplify qx at 1/8 and interpret what this means in a rate of change. So there's a find part and an interpret. Find means to get the number. So to get the number qx at 1/8, all that means is everywhere we see an x, we plug in a 1. Everywhere we see a y, we plug in an 8. So this would be 50 times 1 to the minus 2/3 power times 8 to the 2/3 power. Now 1 to any power is 1. Let's review here just to make sure we're all good. What does 8 to the 2/3 mean? The third down here means, squared cubed root. So it would be the cube root of 8 squared. Cube root of 8 is 2. 2 squared is 4, so that would be 200. Now to interpret this as a rate of change, it's just like interpreting a slope. We can write this as a fraction. Think of that as 200 over 1. The numerator is the output units. The denominator is the input. The output here is thousands of units. The inputs are millions of dollars invested in labor. So as a rate of change, for each additional $1 million spent on labor, we can expect an increase in production of 200,000. We can expect an increase because this is a positive number. So take a minute and let me know if that interpretation makes sense. You see where this is coming from? Does it look familiar? It's the same. I mean, you've been interpreting slopes since algebra. It's the same thing. I'll leave number 5 to you. Here we're looking at QY. So once again, you'll find QY to be 50 and interpret QY. So looking at our two partials here, let's say you had additional funds at your disposal and you wanted to invest and get the most bang for your buck. Would you put it into labor or would you put it into capital? And why? So what do you think? QX is 200, QY is 50. Based on that information, if you had extra money left over, or you were going to do an investment in the company, what would you do how would you invest it so as to get the biggest boost in production? What would you do? Would you invest more into labor or invest more into capital based on what you see here? In labor, because for labor, for each additional million, you get an extra 200,000, whereas for capital, for each additional million, you're only getting 50,000. Okay. So if we did that, we would expect an increase of 40 times 200,000 units at 8 million items. However, the actual retail value based on our Cobb-Douglas production model would only be about 2 million items. If we put it all into capital, you'd expect an increase of 40 times 50 or 40 times 50,000, so 2 million items, 2 million units. The actual retail value is actually closer to 2 million. So the reality is you would probably put some into labor and some into capital in order to grow things the best, instead of putting all your eggs in one basket. And this is the problem we're going to come back to later in the chapter when we developed more tools. Because right now we're just looking at derivatives in the x direction and y direction. But what did we talk about yesterday? How many directions are there at any particular point? You follow? There's infinitely many directions. So maybe you invest some into labor and some into capital. What would be the optimal mix? All right, the last one here. Does anyone recognize this? Have you had the chemistry? Have you had chemistry classes? Principles of chemistry, something like that? You remember this one? PV equals nRT. So R is a constant. P represents the pressure of the gas. V is the volume of the gas. N represents the moles of the gas. If you don't know what a mole is, it's kind of like dozen. Mole tells you how many molecules of the gas there are, and T represents the temperature. Well, this is a relationship that describes several functions of several variables. So for example, if I solve the ideal gas law for P, that's nRT over V, I could take the partial derivative of P with respect to V. So if I take the partial derivative of P with respect to V, that treats everything else as a constant. So I could bring the nRT, all that would be out front. And what's the derivative of 1 over V? Minus 1 over V squared, which gets you to here. Now, in like chemistry, holding the other variables as constant means we're keeping the temperature the same, we've got the same amount of gas, and we're just looking at the relationship between pressure and volume. Okay? And what was pressure and volume? What was that, Boyle's law, I think? Okay? You could solve the ideal gas law for V and look at the partial of V with respect to T. So V would be nRT over P, and you could take the partial of V with respect to T. Here, if we're taking the partial of V with respect to T, we're treating all of these folks as constants. So they would come out, and I'd just be taking the derivative of T with respect to T. And what's the derivative of T with respect to T? You follow? And so once again, looking at the relationship between just volume and temperature, I believe that's called Charles's law. And I'll leave this one to you. Rinse and repeat. Solve for T, look at the partial of T with respect to P. And then we have this identity. And this identity can be part of a project. If you're excited about thermodynamics and thermodynamic systems, this is a very important property of the ideal gas law. And systems that have these same sorts of things have this same kind of identity when it comes to their partial derivatives. Okay. I think I don't. If you're taking physics at Lakeland, you probably have Professor Ciferno. I found a paper about modeling the energies of a rubber band as you stretch it, and it kind of was based on this phenomenon. Okay. And here's your homework.